Antenna basics from antenna wave propagation. Types of antennas. As we know that antenna can be used as transmitting or receiving antenna. There are several types of antennas. Among them, the important types of antennas are wire antennas, traveling wave antennas, aperture antennas, reflector antennas, IC type antennas. Here wire antennas have monopole, dipole, loop, helical are there. Traveling wave antennas like Yagi, Yuda, aperture antennas like waveguides and horn antenna, reflector antennas like parabolic reflector, IC type antennas like microstrip, and then wire antennas. In wire antennas, we have dipole antenna, loop antenna, helical antenna. Dipole antenna. The most commonly used antenna is dipole antenna. It is made up of two straight wires or conductors placing along the same axis, with the existing source is kept at the center. A symmetric dipole is produced. Half wave dipole, quarter wave dipole are there in dipole antenna. This is the structure of dipole antenna. And loop antenna. The figure shows a loop antenna consisting of a single turn of the wire forming a loop. Here we have square loop antenna and another square loop antenna and rectangular loop antenna, circular loop antenna, triangular loop antenna. Loop antenna. Again, it is generally excited by a generator. The field produced by the loop antenna is very much similar to field produced by the dipole antenna. Here we have some structures of single turn circular loop antenna, multi-turn rectangular loop antenna, radiation pattern. Helical antenna. This is the diagram for helical antenna. The antenna with a wire in the form of helix supported by a ground plane is called helical antenna. All the three types of antennas mentioned above are wire antennas. They are mostly used in automobiles and aircrafts. Isotropic radiator. In general, isotropic radiator is defined as a radiator which radiates energy in all directions uniformly. It is also called as isotropic source and omnidirectional antenna or unipole or monopole we call it as. The isotropic antenna is used as a reference antenna, but practically none of the antennas radiates energy uniformly in all directions. Note, isotropic antenna can't exist practically. We must know this. Isotropic antenna can't exist practically. Consider an isotropic antenna or radiator is placed at the center of the sphere of radius r. The power radiated by the isotropic source passes over the surface area of the sphere given by 4 pi r square. At any point on the surface area, the radiated power per unit area is given by Poynting vector. This is the diagram for isotropic radiator. The radiated power W by meter square travels in the radial direction, that is P phi equal to P theta equal to 0. The magnitude of Poynting vector will be equal to the radial component, that is modulus of P bar equal to PR. The total radiated power omega is given by P rad equal to double integral P P bar dot ds equal to double integral PR dot ds, and then P rad equal to PR dot 4 pi r square. The radial power is also called as average power density. PR equal to P average. The average power density is given by P average equal to P radial by 4 pi r square. R is radius of the sphere in meters. P rad equal to the total radiated power in watts. P average equal to the average power density in watts per meter square. Irrespective of antenna types and applications, all the antennas have certain fundamental properties. They are radiation pattern, beam solid angle or beam area, radiation intensity, antenna gain, directivity, radiation resistance, antenna beam width, beam efficiency, antenna bandwidth, antenna aperture, resolution, and effective height. Radiation pattern. Practically any antenna can't radiate energy in all directions uniformly. It is found that the radiation is large in one direction and zero or minutes in other directions. The radiation from an antenna is measured in terms of field strength. The field strength is expressed in millivolts per meter. Radiation pattern is nothing but a 3D graph. If the radiation of an antenna is represented graphically as a function of direction, then it is called as radiation pattern. The radiation pattern is of two types. First one, field radiation pattern or field strength radiation pattern. Second one, power radiation pattern. Field radiation pattern or field strength radiation pattern. The graphical representation of the magnitude of the electric field or magnetic field radiated by an antenna is a function of space coordinates. Power radiation pattern. The graphical representation of the power radiated by an antenna as a function of space coordinates. The diagram of field radiation pattern or field strength radiation pattern. The figure shows three-dimensional representation of field radiation of an antenna. Spherical coordinate system is suitable for the representation of field radiation pattern. The radiation pattern of an antenna in any direction is specified by the angles phi and theta. The main lobe on positive z-axis which represents maximum radiation in that direction. The minor lobe or side lobes contains minimum radiation. The radiation pattern consisting a small lobe exactly opposite to main lobe on negative z-axis is called as back lobe. Note that the radiation pattern of an antenna consisting of variations in both electric and magnetic fields, but for the mathematical analysis it mainly includes electric field components only. E theta of theta comma phi indicates theta component of electric field as a function of theta and phi, and it is expressed in volts per meter. E phi of theta comma phi indicates phi component of electric field as a function of theta and phi, and it is expressed in volts per meter. The normalized field pattern is defined as ratio of field component to its maximum value. E theta n of theta comma phi equal to E theta of theta comma phi by E theta of theta comma phi max. E phi n of theta comma phi equal to E phi of theta comma phi by E phi of theta comma phi max. This is the field pattern in linear scale. Next one, power radiation pattern. If the radiation of an antenna is expressed in terms of power, then this graphical representation is called power radiation pattern. PD of theta comma phi, power density per power flow per unit area. The normalized power density in terms of value is given by Pdn of theta comma phi equal to Pd of theta comma phi by Pd of theta comma phi max. Power radiation pattern diagram. The power density can be expressed in terms of electric field intensity. Pd of theta comma phi equal to 1 by 2 into modulus of E of theta comma phi whole square by eta naught in omega per meter square. Eta naught equal to intrinsic impedance of free space. Eta naught equal to 120 pi. The normalized power density is defined as Pnd of theta comma phi equal to modulus of E of theta comma phi whole square by modulus of E of theta comma phi whole square max. These are the power radiation in linear scale and power radiation in dB. Radian and steradian. Plane angle. The angle between two lines meeting at vertex. The units of plane angle is radians. Plane angle is analogical to 2D space. Then solid angle. The angle sustained by an object in 3D space from a point. Solid angle is analogical to 3D space. The units of solid angle is steradians. The basic difference between radian and steradian is radian is the measure of the plane angle and steradian is the measure of the solid angle. 1 steradian equal to 1 radian square, that equal to 180 pi by pi whole square. Radian and steradian of circle and sphere we have. Here ds equal to r square d omega and d omega equal to ds by r square. Let us consider a sphere of radius r with differential surface area of the spherical coordinate system is given by ds equal to r square sin theta d phi. Let ds equal to r square d omega, then d omega equal to sin theta dot d theta dot d phi. Beam solid angle mu a. Beam solid angle is defined as the integral of normalized power density over a sphere, and it is given by mu a equal to integral theta and integral phi pdn of theta comma phi d omega. Omega a equal to double integral theta and phi pdn of theta comma phi sin theta d phi. Note that beam area or beam solid angle is denoted by mu a and units are steradians. Radiation intensity. It is denoted by U and is defined as power flow per unit solid angle. The radiation intensity is expressed as watts per steradian. U of theta comma phi equal to r square pd of theta comma phi. Pd of theta comma phi is Poynting vector or average power. The total radiated power in terms of radiation intensity is given by P radial equal to double integral theta and phi pd of theta comma phi ds. ds equal to differential surface area. P radial equal to the total radiated power in watts. Pd of theta comma phi equal to average power density watt per meter square. ds equal to r square sin theta d phi. P radial equal to double integral theta and phi pd of theta comma phi r square sin theta d phi. u of theta comma phi equal to r square pd of theta comma phi, and p radial equal to double integral theta and phi u of theta comma phi ds. The average radiation intensity is given by u average equal to p radial by 4 pi. The normalized power density in terms of radiation intensity is given by Pdn of theta comma phi equal to u of theta comma phi by u of theta comma phi max. Directive gain. It is the ratio of the power density to the average power radiated by an isotropic antenna. Gd of theta comma phi equal to Pd of theta comma phi by P average, that is the first equation. For isotropic antenna, P average equal to P radial by 4 pi r square. This is the second equation. Gd of theta comma phi equal to Pd of theta comma phi by P radial by 4 pi r square. Then r square Pd of theta comma phi by P radial by 4 pi. If P radial by 4 pi is equals to U average, then P r square Pd of theta comma phi is equals to U of theta comma phi, that equals to U of theta comma phi by U average. Gd of theta comma phi equal to U of theta comma phi by U average. U of theta comma phi equal to radiation intensity. U average is equals to average radiation intensity. Directivity D. The ratio of the radiation intensity in a given direction from the antenna to the radiation intensity averaged over all directions, D equal to U max by U average, that equals to first equation, and U average equal to P average by 4 pi, that is second equation. Substitute U average in equation 1. D equal to 4 pi U max by P radial, that is third equation. We know that U of theta comma phi equal to R square Pd of theta comma phi. U max equal to R square Pd of theta comma phi max, that is equation 4. Substitute equation 4 in equation 3. Therefore, D equal to 4 pi R square Pd of theta comma phi max by double integral Pd of theta comma phi ds, that is fifth equation. Since ds equals to R square d omega, D equal to 4 pi R square Pd of theta comma phi max by integral double integral Pd of theta comma phi dot R square d omega, that is the sixth equation. Then that is D equal to 4 pi into 1 by double integral Pd of theta comma phi d omega by Pd of theta comma phi max, that is the seventh equation. Then D equal to 4 pi into 1 by double integral Pdn of theta comma phi d omega, that is the eighth equation. Since omega a equal to double integral P dn of theta comma phi d omega, therefore D equal to 4 pi by mu a. This is the ninth equation. లైక్ చేయండి, షేర్ చేయండి. మరిన్ని వీడియోస్ కోసం మా ఛానల్ని సబ్స్క్రైబ్ చేసుకోండి.